Chemical equilibrium. Equilibrium is a state of balance. A chemical equilibrium occurs when you have a reaction, you have some reactants and you have some products, and the reactants are reacting to make products at the same rate as the products are breaking down to make reactants. Any reaction can reach that equilibrium state. A moment in which, and if you think about it, it kind of makes sense in the sense that at the beginning you only have reactants and you have no products. So the reactants there are lots of reactants and they collide with each other and they make product. And at some point, the product, you have a lot of product and you have less and less of the reactants. And typically, if the product can go somewhere else, let's say it's a gas and it leaves the reaction vessel, or maybe it's a solid and it precipitates at the bottom of your beaker, that's fine. But imagine that you are in a closed container. So the product has nowhere to go. There is a moment that that product is still there and it will start colliding with each other and it will start reacting back to give you the reactants. And at some point, those two reactions will happen at the same speed. That can happen with any reaction in theory. In practice, tend to happen even if you are not in a closed state. In most cases, we don't have a closed state. In most cases, we do our reactions in an open vessel, in a beaker, in a flask of some description, in a conical flask. However, there are reactions that will still reach that state of equilibrium, even if they are not particularly trapped. And they tend to be reactions in which the products are more stable than the reagents. That's why the reaction happens, but not that much more stable. So at some point when you have enough of the product, it reacts back to give you the reagents. And we call those reversible reactions. So a reaction in which the products are not much more stable, they are more stable than the reagents, but not much more stable. And at some point, the products will start reacting back to give you the reagents. And at some point, that rate of creation and destruction of the product will be the same. So we reach what we call an equilibrium, a dynamic equilibrium. So it's not that nothing is happening. It's not that the reaction has stopped. No, the reaction keeps going all the time. It's just that it goes backwards and forwards at the same rate. So you end up with some sort of fixed amount of the different chemicals, reactants and products, but it's not because they're not reacting. No, they're reacting all the time, just at the same speed, going forwards and going backwards. And we signify that, and the way we show that in a chemical reaction is by using a double arrow. So we can have, we tend to have a double arrow, or sometimes people will use an arrow with two heads. Bear with me a moment because this slide packs a punch, but hopefully we can talk you through it. So let's imagine the reaction I was mentioning before, the decomposition of N2O4, the nitrogen tetroxide, into 2 molecules or 2 moles of nitrogen dioxide. You will have the forward reaction, which is going from the N2O4 to the 2 moles of NO2, and that will have a particular reaction rate dependent on the concentration of N2O4. And then you have the reverse reaction, which is the 2 moles of nitrogen dioxide merging to form N2O4. And that again has a different reaction rate, which is depending on the reagent. And in this case, the reagent for the reverse reaction is the nitrogen dioxide, and to the power of 2 because of the coefficient. So when the reaction reaches equilibrium, it means the rate going forward is the same as the rate going backwards, and that is what I write here. So the reaction does not stop, as the slide says. It's just it goes backwards and forwards at the same rate. Those two speeds are the same. And if we just simplify this and rearrange it, so all the concentrations are on one side and all the constants are in the other side of the equilibrium, or of the equal sign, you end up with this. And we don't call this constant forward divided constant of reverse reaction, we just call it K, and that's it. So the equilibrium constant depends, as you can see, of the concentration of the products to the power of whichever product, to the power of whichever coefficient it is, divided by the concentration of the reagents, the product of the concentration of the reagents, so the product of the concentration of all the products, each of them to its coefficient, divided by the product of the concentration of the reagents, each of them to the power of whichever coefficient they have, and that gives you an equilibrium constant, K, which is experimentally measured. And it depends on temperature. Temperature affects, because it affects the speed of the reaction. So in the moment it affects the speed of the reaction, it affects the reaction rate, it affects both rates, forward and reverse, and it will affect when that equilibrium will be reached. When a reaction is reversible, when it has this tendency to what I call get stuck, when the products react back to give you the reagents, it doesn't matter how you start the reaction. It will take longer, it will take shorter. At some point, a reversible reaction will reach equilibrium. So here I've got the example of the Haber process, which is the industrial process to produce ammonia, starting from nitrogen and starting from hydrogen, both in gas form, to give you 2 moles of ammonia, again in gas form. And it doesn't matter if you start, okay, well, I'm going to start having hydrogen and nitrogen, and don't know if you can see it very well, but the concentration of the hydrogen is higher than the nitrogen because you need 3 moles of hydrogen per mole of nitrogen you make, and you start with no ammonia. Or if you just decide to be random and say, okay, well, I'm just going to use ammonia and see what happens, and you have no nitrogen or hydrogen. Eventually, when the reaction starts, you can see here the concentration of the hydrogen and the concentration of the nitrogen start decreasing, and the concentration of the ammonia start increasing because the reaction is happening. At some point in time, equilibrium, there will be enough ammonia to start reacting back, to break down into nitrogen and hydrogen, and at some point those 2 rates of formation of ammonia and the breaking down of ammonia will be achieved. Equilibrium will be achieved. The time will be different. It will depend. Well, we'll look at it. We will look at what you can actually do to play with how long it's going to take you to reach equilibrium, and the quantities individually of hydrogen, ammonia and nitrogen might be different, but the fact that they are at equilibrium and the reaction goes backwards and forwards at the same rate, that is, it cannot be changed because this is a reversible reaction.